Today, I will reveal a transformative geometric system, one where the golden ratio's geometric properties allow us to construct perfectly precise forms, completely independent of pi, free from approximations, and requiring no numerical computation. We'll discover how circles naturally give rise to spheres, how spheres generate cubes with integer surface areas, and how these forms interconnect through fundamental geometric laws. You'll witness how from a single circle, we can derive a perfect square. From that square, extract the golden ratio, and from this ratio, regenerate the original circle with exact precision, all unfolding within a self-referential, fractal geometry where every element maintains harmonic order and infinite scalability. What follows is not merely a drawing exercise. It is an invitation to rethink how we understand proportions and space. Now, we will dive into the geometry of light, into the construction of truth, where the straightedge and compass are transformed into instruments of revelation. I will show how this ratio, both mathematically precise and mysteriously profound, can be recreated in structures that embody the same aesthetic found in nature itself. Throughout the history of mathematics, one number has always stood at the center of attention: the number pi. It has long been considered the foundation of our understanding of the circle, the key to precise calculations and, notably, a symbol of the nonlinear yet rigorously defined nature of the universe. Pi has been mathematically proven to be a transcendental number, meaning it cannot be expressed through a finite sequence of basic operations, and therefore it cannot be constructed with a compass and straightedge. Meanwhile, another number, perhaps even more mysterious, has lingered quietly in the background: the golden ratio. This ratio has fascinated artists, architects, and naturalists for centuries. We find it in the arrangement of flower petals, in the spirals of shells, in the proportions of the human body, even in the structure of galaxies. And yet, in mathematics, especially in the formal, construction-based tradition, the golden ratio has been surprisingly underused. Why? Perhaps because it wasn't immediately associated with circles. Because it was not a part of the standard Euclidean toolkit. Because everything revolved around the value of pi. But what if we've been looking in the wrong direction all along? In this introduction, I would like to begin by demonstrating the fundamental relationships between the circle, triangle, and square. We will start with a circle with a radius of 1 millimeter. From its radius, we construct a square and denote its side length as a. Now, we find the midpoint of the square side and draw a diagonal from this midpoint to the opposite corner, and then transfer this diagonal length to the baseline. This length is the square root of 5 divided by 2. We denote this shorter length as b. In this case, we have scaled the original length a by the golden ratio. The golden ratio is a special proportion where the ratio of the smaller part to the larger part is equal to the ratio of the larger part to the whole. Mathematically expressed, if we have lengths a and b, where a is greater than b, then the following holds true. This ratio is 1.61803398887, which can also be written as the square root of 5 plus 1 divided by 2. This ratio creates perfect harmony because each part carries within it the structure of the whole. By transferring the diagonal, we obtain a new point on the baseline, from which we now construct the first golden circle. This very circle will determine the key ratio relative to the square of the original circle. For the square, we know its area is exactly 4 square millimeters. The area of this circle is not approximately 1.1999 square millimeters, as conventional calculations would suggest, but precisely 1.2 square millimeters. This discrepancy arises from the incorrect tolerance of the value of pi in standard computations. This area of 1.2 square millimeters represents a quasi-integer value, which will later allow us to construct circles with precisely defined integer-like area properties. As a result, the areas of the square and the circle are in an exact ratio of 10:3. The base area of 1 square millimeter is now divided in a ratio of 7:3. The larger part occupies 0.7 square millimeters, 7/10 of the whole area, while the smaller part occupies 0.3 square millimeters, or 3/10 of the whole area. If we construct a golden sphere from this golden circle, its surface area will be exactly 4.8 square millimeters, 4 times the area of the original circle. And in this case, the cube has an area of 24 square millimeters, meaning the cube's surface area is 5 times larger than that of the golden sphere. This is crucial, as it allows us to construct cubes with integer surface areas without the need for computational operations. Now, let's examine this from the perspective of the golden triangle. If we assemble a geometric triangle where one side is the radius and another the diameter, its diagonal will be the square root of 5. This diagonal square root of 5 is essential to the construction, as it inherently contains fractals, which are natural fractals of geometric constructs. The perimeter of this triangle square root of 5 plus 3 can be interpreted as the sum of 10 fundamental fractal segments. This means the length of each fractal segment is square root of 5 plus 3 divided by 10, which can always be constructed and subdivided. On the circumference, this length represents one of the 12 equal arcs of the base circle, while the total perimeter of the triangle consists of 10 such arcs. This ratio thus forms the transition from square geometry to circular geometry via the triangular form of fractal divisions. If we consider the base length of 1 as a unit, this geometric transformation represents an expansion of the perimeter in a 6:5 ratio. We interpret this as adding 1/5 of a unit to the base structure, a principal characteristic of natural growth, the golden ratio, and fractal branching. From these ratios, we could derive further formulas, though they won't be necessary here, as we'll resolve the problem entirely through construction. Next, we'll construct a golden square from the base circle, revealing additional ratios. As before, we measure the diagonal, transfer it to the baseline to mark a new point, create a circle, and from it, a square. This golden square has an area of 10.472 square millimeters and maintains a 10:3 ratio to the circle's area. Consequently, it also relates to the circumference of the base circle in a 5:3 ratio. If we now construct a cube from this square, the resulting cube has a surface area of exactly 62.8328157 square millimeters. Meanwhile, the circumference of the circle, or the surface curve of the sphere, calculated using the earlier formula, gives us the value of 6.8328157 millimeters. Although the surface area of the cube and the circumference of the circle belong to different dimensions, square millimeters versus millimeters, their numerical values are in a precise 10:1 ratio. That is, the numerical value of the cube's surface is exactly 10 times the numerical value of the circular or spherical circumference as derived from the golden ratio-based formula. Between the volume of a cube and a sphere, no particularly notable ratios are observed, except that when calculating with the new volume formula, a sequence of identical numbers appears. This repetition of numbers, this seamless transition from lengths to areas and then to volumes, is a constant feature. It reveals a persistent emergence of identical numerical values, or fractals, flowing between different geometric forms. The numbers themselves remain unchanged, only the foundational shape transforms, whether it is a circle or a cube. This phenomenon, while rooted in pure geometry, hints at deep implications for number theory. It suggests a hidden numerical structure that transcends traditional mathematical categories. However, this video will not explore that aspect. When working with ellipses as geometric constructs, this same proportion generates a golden rectangle. Here, we extend the semi-axis by the golden ratio to create the rectangle. Crucially, the 10:3 area ratio remains invariant regardless of the ellipse's eccentricity or orientation. As demonstrated thus far, the golden triangle, golden square, golden circle, and golden rectangle form a self-contained geometric system. Each element derives from the same invariant ratio, maintaining a fractal relationship to the base unit, 1. This enables the recursive construction of new shapes without proportional loss. Hidden within a simple arrangement of overlapping circles lies one of the most profound and ancient symbols known to humanity, the seed of life. Though it appears deceptively simple at first glance, this sacred geometry reveals a timeless language, one that speaks of creation, proportion, and the very architecture of the universe. The seed of life is not just a symbol. It is a fundamental structure from which all forms emerge. It echoes through nature, from the spiraling galaxies above us to the cellular patterns within us. Its precision is not the result of artistic whim, but of deep mathematical order rooted in the harmony of number and geometry. Today, we will explore this pattern not as myth or metaphor, but as a functional geometric system that reveals measurable truths that challenge classical assumptions and offer a new perspective on space, form, and even constants like pi. Prepare to see how this ancient pattern holds the key to unlocking the universal code behind natural growth, symmetry, and balance, and becomes a bridge between ancient wisdom and modern mathematical precision. We begin with a base circle with a radius of 1 millimeter. We find its center, have the radius, and use that midpoint to construct a diagonal from which we draw the golden circle. If we then continue drawing circles of the same radius around the perimeter, we create the seed of life. This pattern, through its intersections, both between the circles themselves and with the original circle, naturally creates points from which almost all regular polygons can be constructed. These colored arc lengths represent the arc lengths of the polygons. The seed of life contains also archetypal distances that appear regardless of the initial radius. The seed of life is constructed within a base circle of exactly 1 millimeter in radius. Regardless of the radius used to draw the internal overlapping circles, all intersections that occur on the boundary of this 1 millimeter circle generate precise distances and chord lengths. These distances do not depend on the internal radius used for the seed of life pattern. They emerge from the consistent interaction between the internal geometry and the fixed outer boundary. As a result, specific geometric values such as 1, 2, and the square root of 3 consistently appear. This reveals a hidden order. The structure of these lengths is embedded in the geometry of the circle itself, proving that certain distances are not relative, but absolute, defined by the seed's relationship to the fixed base circle. For example, if we create a seed of life using circles with a radius of 0.6 millimeters, we find not only these classic distances, but also a length of approximately 1.666, or exactly 10/6 of the unit. This hints at a deeper harmonic pattern in which the number 10 functions as a fundamental scaling constant. In this sense, the seed of life encodes stable natural distances in its pure geometry, forming a foundational layer for higher fractal levels, without requiring any algebraic formulation. A particularly remarkable case arises with the radius of 0.7 millimeters. This specific value leads to a unique geometric transformation that preserves structural coherence, something not observed with other radii. In addition to the universal distances of 1 millimeter, 2 millimeters, and square root 3, another key length emerges, 10/7. This line segment, which connects two significant intersection points, lies precisely along the inner circle's circumference, a geometric alignment found only with the number 7 in this configuration. This allows for a seamless geometric transfer from one circle to the next, using the same 10/7 segment as a bridging diagonal. When this segment is rotated around its origin, its endpoint lands precisely on the circumference of the base circle, remaining in perfect alignment with the inner circle. Through this process, a new layer of circular construction emerges, still fully harmonious, revealing two alternating petal patterns. This dynamic reveals that the 0.7 millimeters radius uniquely allows a transition between fractal layers through rotation, all while maintaining full geometric coherence. This phenomenon is likely linked to natural harmonic resonances, similar to those observed in sound, light, and organic growth patterns. Therefore, the 0.7 millimeters radius deserves thorough mathematical, geometric, and physical analysis, as it may unveil a profound harmonic principle embedded in the fundamental geometry of life. Using the seed of life, we can also easily scale up circles and their corresponding squares. This is a simple linear progression of 1x, 2x, 3x, and 4x the base area. If the base circle has, for example, an area of 1 square millimeter, then the next circle in the sequence has 2, the third 3, and the fourth 4 square millimeters of area. To construct these expansions accurately, we must understand how a circle's area increases with the square of its radius. For this reason, we shall now visualize this process. We start again from a circle with radius 1 millimeter. From its center and a point on the edge, draw a vertical line, parallel to the y-axis. This line defines the roots of whole numbers geometrically, without any calculations. The first diagonal corresponds to square root 2, the next to square root 3, then square root 4, and so on. With each step, the area increases by the square of the respective root. So for example, the square root of 7 results in 7 times the base area. In this case, we derive the square root geometrically and construct it accordingly. All values remain exact, without any approximation of pi. The method is based on invariant ratios and proportional scaling between a circle and a square, allowing precise constructions without numerical calculation. Alternative scaling methods rely on dividing the upper half of the base circle's square side into multiple possible partitions, depending on requirements. In this specific case, we'll focus on dividing this length into 10 equal parts. By doing so, we create natural intersection points that allow controlled scaling. The first point gives a 1% increase, the second 4%, the third 9%, and so on, up to 100%. This forms a natural square-based progression of surface growth. This method reveals the profound symmetry between circles and squares, where roots and areas emerge purely through geometry, untouched by approximation. By harnessing the circle's innate proportions and scaling them through the square's diagonal hierarchy, we achieve perfect integer relationships. Every square root n constructs an area of n. Every partition preserves exactitude. Here, mathematics sheds its computational skin and returns to its geometric essence. A system where ratios reign supreme, pi becomes irrelevant, and growth follows the immutable laws of spatial logic. So far, I have shown how the areas of circles and squares can be increased using the golden ratio. Now, I would like to explore how this ratio can also be observed in the circumferences of circles. Once again, we begin with a base circle with a radius of 1 millimeter, and we inscribe within it its golden circle. Now, let us inscribe a golden circle within the original one, meaning a new circle whose circumference is not approximately 2.3999 millimeters, but exactly 2.4 millimeters, a clean, rational value. This suggests that the construction of golden circles naturally leads us to numerically whole-valued circumferences, which is extremely useful for further geometric constructions. Manipulating circumference is significantly more straightforward than manipulating area, as circumferences can be increased or decreased linearly based on simple divisions of the radius. However, it must be done in a geometrically accurate way. For example, if we now have a circle with a circumference of 2.4 millimeters and we wish to reduce it by 0.4 millimeters, we can proceed as follows. Divide the radius into 12 equal parts. Select the second segment, which is 2/12 or 1/6 of the original radius, and use it to construct a new circle. This new circle will have a circumference of exactly 2 millimeters. In this case, we have reduced the circumference by 1/6. Since the circumference is proportional to the radius, dividing the radius into 12 equal parts and using a shorter segment reduces the circumference by the same fractional amount. 1/12 of the original radius corresponds to 1/12 of the circumference. The same logic applies when we increase the circumference. To increase the circumference by a fixed amount, say by 1/12 of its current value, we project the radius outward from the circle's circumference, effectively extending the diameter by 1 radius length. Next, we divide this radius length extension into 12 equal segments to establish the scaling units for the circle. We then add one of these segments to the original radius and use this longer length to construct a larger circle. In this way, we can accurately scale up the circumference in steps of 1/12, or by any other desired fraction, depending on how the radius is subdivided. Because length grows linearly, while area grows quadratically with respect to the radius, lengths are ideally suited for precise and incremental scaling, both upward and downward. This makes circumferences a powerful and manageable tool in geometric construction when working with exact proportions and natural ratios like the golden ratio. Rather than relying on abstract equations, this visual and geometric approach reveals a tangible rhythm of growth, where each step corresponds to the square of its position. It's a harmonious system, unfolding like a geometric heartbeat, predictable, elegant, and universally applicable. Such scaling is not only efficient, but also rooted in the very logic of nature's design, offering a bridge between visual intuition and mathematical precision. As we continue our journey through the geometry of creation, we now enter a deeper layer, one where patterns repeat, scale, and echo across dimensions. This is the realm of fractals. Fractals are more than just complex shapes. They are nature's blueprint for self-similarity and endless depth. But here we encounter a new kind of fractal, one born not from chaos, but from perfect order. These are not random repetitions, but intelligent recursions that reveal a hidden logic behind growth, harmony, and structure. Let us now unfold this hidden geometry and follow its path through fractal expansion. As I demonstrated earlier in this video, the circle's circumference is composed of 12 fundamental fractal elements. Now, I will reveal how these same fractals manifest as intricate surface patterns. When we observe the basic structure composed of 3 consecutive squares, where the first square has a side length of 0.1 millimeters or 1/10 of the circle's radius, the second square has a side extended by the golden ratio, measuring 0.16180,339 millimeters, and the third square combines the previous 2 lengths, resulting in a side of 0.26180,339 millimeters. We encounter a proportion that forms the foundation of all subsequent fractal growth. The first and second lengths are in the ratio of 1 to phi, while the second and third follow the same rule, thus forming a sequence of lengths that follows the logic of natural growth, as known from the geometry of the spiral, where each subsequent value is derived by summing the previous 2. This principle forms the foundation of what we may call golden fractal geometry, a layered system of geometric scaling where each level is connected to the next by phi, either in the form of multiplication or fractional transformation. Each square constructed in this geometric system, following the proportions derived from the golden ratio, extends one of its sides upward, creating a directional ray that intersects the circumference of the main circle. Critically, these extensions arise not only from the golden cut points of each side but also from their precise midpoints, a dual generative process that ensures harmonic division. These intersections are not random or arbitrary. Rather, they are precisely determined by the internal mathematical logic of the golden ratio, where every midpoint-derived ray complements those from phi division, together weaving a fractal lattice of angular relationships. The extended side of each square acts like a projection vector, originating from a single base point and reaching out toward the boundary of the circle, where it meets the circumference at a specific point. These points of intersection form a discrete spectrum along the circle's edge, and their radial distances from the origin correspond to well-defined mathematical expressions involving the square root of 5. The fractal squares exhibit a remarkable growth pattern where each iteration follows an exact mathematical progression. With every new fractal generation, we observe that the area scales by integer factors while the side lengths follow the square root of these integers, a fundamental relationship emerging from the system's geometric core. For the second fractal square, the area indeed doubles, a factor of 2, while its side length increases by square root 2. But this is just the beginning of an infinite sequence. The third square triples the original area, factor 3, with side length scaling by square root 3. The fourth square quadruples the area, factor 4, with square root 4 scaling, and this pattern continues perfectly through all subsequent iterations. This precise integer to square root relationship doesn't occur by chance. It arises because each new fractal square's area represents the sum of all previous areas in the sequence, while the side lengths maintain quadratic proportionality. When we project construction lines from both the golden ratio points and midpoints of each square's sides, these exact scaling factors automatically ensure that every new intersection point on the circle's circumference maintains perfect harmonic alignment with all previous points. The system's elegance lies in how this growth pattern, areas increasing as integers and lengths as their roots, creates an infinite, perfectly self-similar fractal structure. Each new generation nests precisely within its predecessor's framework, maintaining all golden ratio proportions while exhibiting this exact mathematical progression at every scale. As we follow this transformation, a deeper pattern begins to emerge, one that reveals the conversion from circular to square geometry. When we reach the sixth fractal, the side length of the largest square is exactly square root pi. This third square intersects the original circle at a precise point of area equivalence. Building a square on this square root pi segment then produces a figure whose area is precisely equal to that of the circle, without any approximation or numerical estimation. Here, the circular form and the square converge in area, even though their shapes remain distinct. This process does not approximate or estimate. It defines and generates exact equivalence through proportion and projection, allowing us to witness the seamless transformation of circular space into square geometry. This sixth fractal thus serves as a turning point. It's where scaling, symmetry, and proportion converge into a single principle, the principle that space itself can be organized by pure number and geometric resonance. This is also reflected in the fact that none of these squares stands as a closed unit, but each contains an openness toward further development, which means that from the very beginning, it is constructed as a fractal. And since this fractal is based on a constant phi ratio, we can rightfully say that the law of all future growth is already encoded in this foundation. When we examine the construction of this sixth fractal, which generates an area precisely equal to its containing circle, we observe it originates at 0.6 millimeters, exactly 3/5 of the radius. This critical proportion enables us to construct squares with integer surface areas directly from circles using purely geometric methods, completely eliminating computational calculations. In this sense, we are no longer speaking of geometry in the usual sense, but of a geometry of meaning, where each length expresses something and has a reason for its existence. There exists in geometry a harmony so perfect, so universal, that it whispers through the spirals of galaxies and the curve of seashells alike. This is the golden angle, approximately 137.5 degrees, a precise geometric division that transforms a simple circle into a masterpiece of mathematical artistry. When we divide a circle according to the golden ratio, this special angle emerges as if by magic, creating arcs whose proportions mirror the infinite beauty of nature's design. What makes this angle extraordinary is not just its mathematical elegance, but how it serves as a fundamental growth pattern in our universe. It appears in the arrangement of sunflower seeds, the curl of fern fronds, and even the path of hurricanes, a universal constant hidden in plain sight. The golden angle represents nature's most efficient packing algorithm, its most graceful solution to the problem of growth and form. Let us now examine a unit circle with radius 1 millimeter, from the perspective of angular division by the golden ratio. The golden angle arises when a full circle is divided into two arcs such that the ratio of the smaller arc to the larger arc is equal to the ratio of the larger arc to the full circle. Mathematically, this gives the well-known golden angle, 137.5077 degrees. In a unit circle, where circumference is 6/5 the square root of 5 plus 3, this angle corresponds to a shorter arc of 2.4 millimeters. The longer arc, then, is the complement, 6/5 the square root of 5 plus 1. The shorter arc is a rational number, 2.4 millimeters, while the longer arc remains tied to an irrational golden expression, combining square root of 5. Now, let us inscribe a golden circle within the original one, a new circle whose circumference equals that 6/5 the square root of 5 plus 1 millimeters arc. This circle again splits into a golden ratio. The longer arc now becomes exactly 2.4 millimeters, while the shorter arc is a further fractalized segment related again to square root of 5. This recursive scaling process continues. Each next circle can be divided according to the same ratio, resulting in an infinite golden subdivision structure, a logarithmic spiral of arc lengths. Through this recursive construction, we consistently return to the number 3. This number seems to stabilize and repeat, suggesting that 3 is not only a numerically central figure, but also a structurally generative number in natural forms. It appears in symmetries, tilings, and rotation sequences, forming the backbone of organic fractal growth. This remarkable system shows us that the golden ratio isn't just a static proportion, but an active, generative principle, an algorithm for infinite construction that maintains perfect proportions while alternating between exact and irrational values. The appearance of 3 as a stabilizing factor suggests deep connections to other areas of mathematics and physics, where threefold symmetry often appears as a minimal, optimal configuration. Up until now, we've explored how to create circles with integer surface areas, how to precisely scale their dimensions, how to achieve circumferences of whole numbers, and how to transform them into larger or smaller forms, all while maintaining perfect geometric harmony. We've also uncovered the method to construct a square with the exact same area as any given circle, purely through proportional geometry, without relying on numerical calculations. Now, let's bring this theory to life. We'll begin by constructing a circle with an area of 9 square millimeters, a whole number rooted in our scaling principles. From this circle, we'll derive a square of equal area using only compass and straightedge, thereby proving the validity of our geometric claims. Every step will confirm what the mathematics has already revealed, that these constructions are not approximations, but exact manifestations of an inherent order. Watch closely. As the circle surrenders its area to the square, the invisible bonds between curved and straight lines will become visible, and the truth of our method will emerge clear and undeniable. Now, let's create a circle with an area of exactly 9 square millimeters. We begin with our base circle, which has a radius of 1 millimeter. We then have this radius and transfer this diagonal length to the baseline. Through this point, we draw a golden circle with an area of 1.2 square millimeters. We will now increase this area by 25% or 5/4. In this case, we first divide the upper half side into 2 equal parts, giving us the midpoint of this length. Then, through the center and this point, we construct a circle. If we now measure this digitally, its area is 1.5 square millimeters. Next, we simply increase this new circle's area by 100%. We do this by drawing a circle from the center to the edge of the square's circle. This creates a new circle whose area, as we can again measure digitally, is now 3 square millimeters. To reach 9 square millimeters, we simply triple it. In this case, we now easily construct the seed of life pattern from these circles, where the third circle in the sequence then creates our desired surface area of exactly 9 square millimeters, not 8.9998 square millimeters, as tolerated by the digital computer calculation. To verify this, we will now construct a square with the same area. The construction of this square starts from 3/5 of the radius. We divide the radius of the circle into 5 equal parts. This method of division has been known in mathematics for a long time. From the starting point of the radius, we draw an arbitrary oblique line. On this line, we construct a sequence of circles with equal radii, which create intersections along the line. Then, we connect the 5th intersection to the end of the radius. Through the remaining 4 intersections, we draw lines parallel to this connecting line. In this way, the original radius is divided into 5 equal parts. Next, we take 3 of these segments and use them to construct the first square. This square serves as the base length for further construction. We find the midpoint of its side and transfer that point to the base. Then, using this new length, we construct a new square. With this, we have scaled the original length by the golden ratio. We repeat the process. Find the midpoint again, project it to the base, and construct a third square. In this way, we have scaled 3/5 of the original radius twice by the golden ratio. As I demonstrated earlier, this third square intersects the original circle at a precise point of area equivalence. The length from the beginning of the square to this point of intersection represents now the side of the square with the desired area. If we measure this length precisely, we find that it equals exactly 3 millimeters. With this length, we can now construct a square whose area is 9 square millimeters. Given that we have successfully constructed a square with the exact same area as a circle measuring 9 square millimeters, we can now observe a remarkable proportional relationship. When we measure the surface area of the inner square, the central square in the construction, it turns out to be precisely 2.7 square millimeters. This value is exactly 30% of the original area, or a scaling factor of 3.33, relative to the full circle. Not only does this confirm the correctness of the transformation from circle to square, but it also reveals a harmonic subdivision embedded in the geometry itself. The number 2.7 is directly related to the number 9 through the ratio 3:1, which mirrors the structural logic of the method we're using, rooted in square-based area progressions and golden ratio scaling. This suggests that the transformation preserves not only total area, but also maintains meaningful internal proportionality, supporting the validity of this geometric framework without relying on pi. Now I will practically demonstrate the construction of the most basic circle, from which we can derive all further circles. A circle with an area of 1 square millimeter. A circle with such an area begins to be constructed from 1/3 of its radius. So first, we divide its radius into 3 equal parts. From the center and through the point at 1/3 of the radius, we draw a circle. To this circle, we now inscribe its golden circle, which already inherently contains whole numbers, although we can express them as irrational numbers. This golden circle will then, through its scaling, transform irrational numbers into whole numbers. This circle has an area of 0.13333 square millimeters, which represents 2/15 of our desired area. We now increase this area by 25%, or 5/4, and in this way we create a circle with an area of 0.16666 square millimeters, which represents 1/6 of our desired area. If we now double this area, simply from the edge of its square, meaning a 100% increase, we create 1/3 of the desired area, or 0.3333 square millimeters. Now, we simply enlarge this circle by a factor of 3 using the seed of life pattern, and we have consequently created a circle with an area of exactly 1 square millimeter. As I have shown earlier, this circle can now be easily expanded progressively. In this case, we need the y-axis where the first intersections will be, and then its parallel from its perimeter where the new intersections will occur. Now we simply draw horizontals from the perimeters of the circles on the y-axis to its parallel, and through the centers in these points we construct circles which then naturally intersect circles on the parallel in points, through which we again create further circles, and thereby increase the base area by 1 time, or in our concrete case by 1 square millimeter. If we now computationally measure each circle individually, we observe that the first circle has an area of 1 square millimeter, the second circle 2 square millimeters, and so on, and if we measure the 9th circle, we find its area to be 9 square millimeters. In this way, we can consequently also create spheres with whole number surfaces, although I do not find it necessary to demonstrate this, since the surface area of a sphere is 4 times greater than the surface of a circle. So if we want a sphere with such a surface, we must create a circle with 4 times smaller area. Now I will demonstrate how we can use this progression to construct a cube with whole number surfaces, without using any calculations. Let us say that our goal is to create a cube with a surface area of exactly 100 square millimeters. According to classical mathematical methods, this would require a calculation to determine the side length of the square, which would then allow us to construct the cube. In our case, however, we start from the simple proportion that I mentioned at the beginning of the video. If we construct the golden cube for the sphere according to the golden ratio, the surface area of this cube will be exactly 5 times greater than the surface of the sphere. Since we want a cube with a surface area of 100 square millimeters, its corresponding sphere must be 5 times smaller. So we need a sphere with a surface area of 20 square millimeters. To construct the sphere, we first need a circle whose area is 4 times smaller than the surface of the sphere. This means we need a circle with an area of 5 square millimeters to construct such a cube. Now, if I use this practical progression that we have created here, we look for our circle with an area of 5 square millimeters. In this case, we simply locate the midpoint along the radius of this circle, which then allows us to scale this length by the golden ratio. We now transfer this diagonal to the baseline and from this point construct a new circle. To this circle, we simply draw its corresponding golden square, which consequently creates a square with exactly the surface area needed for the construction of such a cube. So 6 such surfaces now represent the surface area of a cube with exactly 100 square millimeters. If we now measure the square digitally, the program calculates the value 16.66 square millimeters, which represents exactly 106. From this basic principle, we can now understand something much deeper. If we can construct a perfect circle with a precisely defined area, then we can also use that same principle to construct all other geometric shapes with exactly defined surfaces, not just squares or cubes, but any form we choose. In the universe, where order and chaos intertwine in an eternal dance, the sphere stands out as the most perfect form. It symbolizes harmony, equality, and balance, qualities that inspire us at every scale, from microscopic particles to planets and stars. The sphere is not merely a geometric concept. It is a universal metaphor for perfection and infinity. Classical mathematics often assumes that the surface of a sphere cannot be evenly distributed among the areas formed by meridians and parallels. But this is not the case. I will now present a practical demonstration to prove the opposite, that when we divide the sphere correctly, it is in fact impossible to divide it unevenly. Regardless of how the sphere is segmented, each piece always carries the exact same surface area. Let me show you a method of dividing the sphere, where it is treated as a system of segments in perfect rotation and interconnection. Here we have a sphere with a precisely area of 240 square millimeters. I designed this sphere specifically to demonstrate its division into 15 longitudinal sections and 16 latitudinal bands, a configuration that creates 240 identical surface segments, each measuring exactly 1 square millimeter. This exact division means we're making 15 vertical slices from pole to pole, combined with 16 horizontal divisions around the sphere's circumference. At first glance, the resulting segments might appear to have unequal surface areas. But thanks to modern technology, we can quickly measure each piece, and we find that every segment holds precisely the same surface area. Despite the visible differences in shape, the surface area of each spherical piece remains constant. This is a crucial insight. It confirms that when dividing a sphere, the surface doesn't diminish or increase. It only rotates and redistributes. Now, let's take a look at this second sphere, with a total surface area of 49 square millimeters. I created it to be divided into 7 by 7 parts. Again, when measuring each piece, we find the same result. Surface areas are perfectly preserved, they merely transform. Therefore, regardless of the specific division scheme we apply to the sphere, whether it's a simple 7 by 7 grid or an unconventional 55 by 47 partition, as long as this uniform distribution principle is maintained, all resulting surface segments will maintain perfectly equal areas. This opens up entirely new dimensions of understanding. From these spherical segments, we can derive mathematical relationships that do not rely on classical constants, but rather on internal coherence and the harmonic interweaving of spherical proportions. If we were now to divide the sphere volumetrically, segmenting it in 3 dimensions, this would further clarify how each piece maintains structural balance and symmetry throughout its growth. This type of representation would also become a more powerful tool for analyzing spatial dynamics. However, to fully explore that topic, I would need to double the length of this video. So, I will dedicate a future video entirely to that subject. This means we are no longer limited to abstract formulas or approximations. We now have a tangible visual method of building exact surfaces in geometry, using only the golden ratio as the foundation. Through the progression of golden forms, circles, spheres, and squares, we are able to construct any desired shape with clearly determined whole number areas. This insight opens up new possibilities in both theoretical and practical geometry. Whether we are working with ellipses, polygons, cylinders, or even complex organic shapes, we can now begin their construction from a circle with a known area and expand that area in precise steps, using golden proportions to maintain harmony and measurability. The method also provides a powerful answer to a question that has intrigued mathematicians for centuries: whether it is possible to geometrically construct a square with exactly the same area as a given circle. With this approach, the answer is yes, not only is it possible, but it is constructively demonstrable. And finally, if such a construction is possible in 2 or 3 dimensions, then it also has the potential to serve as a universal geometric language, one that links form, surface, and number in perfect harmony. If you've made it this far, thank you, from the bottom of my heart, for taking the time to explore this journey with me. What I've shared in this video represents months of deep research, intuitive geometry, and countless hours spent building a completely new way of understanding the natural world. I've worked on this project with full dedication and financed it from my own savings, driven only by passion and the belief that this knowledge is meant to be shared freely with others. If this video gave you a new insight, inspired you, or helped you see the universe from a different perspective, then I kindly invite you to consider supporting my work. Any contribution, no matter the size, would help me continue this research and make it possible to share even more knowledge that still lies hidden within the system of nature. You'll find the details for support and donations in the video description below. Thank you again for being part of this journey, and stay curious, because what we've discovered here is only the beginning.